Another interesting force is air resistance. It turns out there's a number of different ways to model fluid resistance, but in general, when an object is moving through the air at a relatively fast speed, we get a force of drag d that is proportional to the speed at which you're traveling squared. There are some other terms here. There's the density of the air, there's the cross-sectional area, and a constant here that just depends on the overall geometry of the system. It turns out that because of this v squared, it's very difficult to solve problems like this in closed form. Many times impossible, and you have to use a computer simulation to get a good answer. But we can get some interesting information. For example, what if we have a person, say a skydiver, falling. What forces will be acting on him? Well, we'll have gravity pulling down, and we'll have the drag force pulling up. When the skydiver first jumps out, what would be the magnitude of d? Think about that for a moment. Do you have an answer? How big is d when he first jumps off the plane? Well, what's the value of his velocity? The moment he steps off the plane, his velocity is 0. It does start to increase soon, but it starts out at 0. So at that moment, the drag force is likewise 0, and he would simply have an acceleration equal to g. However, as he gets very fast, eventually the drag force will increase, and at the very end, the drag force will eventually reach a point where it's essentially equal to the force of gravity. So in that case, drag force minus mg is equal to ma, but at the terminal velocity, these two are equal to each other, so the acceleration will be 0. So we could figure out what's the velocity we need for this. At what velocity does the drag force equal mg? Well, that means 1/2 c rho a v squared equals mg. Solving for v, we get that the terminal velocity is the square root of 2 mg over c rho a, which is exactly what I've got written down here. Now notice that terminal velocity depends on the geometric factor and on the cross-sectional area. So for example, a skydiver in a spread eagle like this has a larger cross-sectional area than a skydiver who is diving like that. So if you put yourself in this position, a straight head down position, you have a smaller area, which results in a larger terminal velocity, and you can fall down faster, catch up to other skydivers who are below. By contrast, when you deploy the parachute, you get a much larger value of the area, which tremendously increases your drag force and lowers your terminal velocity, so that you're actually slowed down when you first deploy it, and you hit the ground at a much lower terminal velocity than you would without the parachute.